So good morning, everyone. I'm here with my partner Jay today, and we'll be talking to you about our fourth-year design project, which involved using conformable heart sensors that were designed using graphene-infused Silly Putty. So if you look at the sort of sensors that we interact with on a daily basis, you can generally split them into roughly three categories. So you have flexible sensors, like the commercial printed FlexiForce sensor you can see pictured above. You have sensitive capacitive sensors, for example, like you'd see on a touchscreen for your cell phones. And more rarely, you'll see something like a textile sensor, which is designed to be highly conformable. So especially as technology is getting better and better, you're starting to see more and more overlap between these categories, but it's very rare that you see a sensor that can cover all three of these categories. So the motivation behind our project was to try and make a sensor that could more cover all of these three categories and be robust in that sense. So in terms of the demand for a sensor like this, so I'm sure all of you are familiar with wearable devices like Fitbits, which are becoming more and more popular because as we get better at handling large volumes of data, being able to collect especially health information is really invaluable. So in terms of just raw markets, Fitbit's growing, or things like Fitbit are growing very rapidly. They're estimated to be worth around $6 billion USD this year, and they're only growing every year. And nearly all of them are somehow related to the heart. So if you look at the way the heart works, there's a lot of really valuable information you can get with respect to just general physiology and health of a human. But we are specifically concentrating at looking not only at heart rate, which is generally the easiest thing to derive from any signal you get from a heart, but also the blood pressure. So the target that we set was looking at the average diastolic pressure, so that's the resting pressure for our heart, and taking half of that. So you can see the average diastolic pressure is around 80 millimeters of mercury, and we set the bar for our threshold that we're looking to get at as 40 millimeters of mercury. So even if you look 2 or 3 weeks ago, Samsung announced their own attempt at this. So something like a blood pressure sensor that could also work as a heart rate sensor is definitely in demand because on top of heart rate, blood pressure gives you a lot of really valuable information about the health of any patient or any individual. But the approach they use is one that you'll see more commonly in traditional or wearable sensors that you'll see today. So generally, they operate on this PPG principle where you're shining a light into a blood vessel or artery and looking at the reflected wave. And from that reflected signal, you can start to derive information about blood oxygen levels, heart rate, and et cetera. Of course, this is actually a pretty good method, especially for heart rate. But like the other technology we've looked at earlier, it's generally limited by the conformability. So if you look at something like an Apple Watch, it's only designed to fit one size. And if it doesn't fit your wrist, for example, or if it's not making good contact, then you start to see difficulties in terms of the data you're collecting.
So in order for us to fabricate a material that meets design requirements, we chose graphene and Silly Putty. The reason why we chose graphene is because it's highly conductive, flexible, and mechanically strong. And also for the reason why we chose Silly Putty is because it's very conformable. And Silly Putty itself is a self-healing polymer. So the first stage of the fabrication process is graphene preparation. First step is dispersing graphite into an organic solvent. In our case, we chose NMP because it's non-volatile and at the same time, it stabilizes dispersion very well. And then we tip sonicate for 72 hours at an amplitude of 60. Now we have graphene in NMP. Next step is solvent exchange. This is required because we want to, at the later stage of the fabrication process, we want to evaporate all the solvent. So in our case, we chose chloroform because it's very volatile and non-toxic at the same time. Next stage is putty preparation. We make silly putty by condensation polymerization method by using PDMS and boric acid. The first step is to heat up PDMS. Once PDMS is heated up, siloxane bond cleaves, and that's when boric acid comes into the place and forms a weak cross linkage. This is what enables Silly Putty to have viscoelastic property, and also results in relaxation timescale of on the order of second. Next is we dissolve Silly Putty that we made into the solvent. And then this is very critical stage because volume to mass ratio is what determines the fill fraction. And we let it evaporate. We let chloroform evaporate for 6 hours at 45 degrees Celsius. And additionally, we let it dry overnight with air. And now we have graphene-infused putty. So the putty that we made has some useful properties. The first one is it is very conductive. When you measure the resistance with DMM, the resistance measurements were ranging from few kilo ohms to few giga ohms. Also, as you can see from the image above, it's very flexible and conformable. To ensure that we have graphene sheets inside our putty, we took some SEM images. They were, as you can see, the mean graphene sheet size were ranging from a sub-micron, and they were conductive.
Okay, so now that we'd somewhat designed our sensor, we're interested in looking how we could test it. So we used a relatively basic setup to test it. And the general idea here is you have a load tester that's applying a normal force to the active area of the sensors. And we have a digital multimeter that's looking at the current that's changing as a result of that pressure. So the way we've designed this sensor, the resistance will change as you apply the pressure due to changes in the network that's making the polymer conductive. So the way we used our sensors, we had a commercial printed flexible sensor to compare to our flat putty disc that we made to match the same active sensing area as the commercial sensor that we were comparing it to. So once the setup was in place, the tests were ran using a data acquisition software made in LabVIEW, and that would let us collect both the input data in terms of the force that we're applying, the normal force, and the output data. And of course, we're looking at the current because at a constant voltage, we'll see the change in current as the resistance is changing. So you can see pictured on the left there, it's just a simple normal force being applied from the top, and the two needles from the side are allowing the DMM to look at the change in current. Okay, so if you take a closer look at the mechanism for how this current is changing, in nearly any conductive material that has any resistance, we'd expect to see a change in resistance when you see a change in geometry. And that's also the case for our sensor. So if you have a 3D putty shape and we apply a normal force, we'd expect to see it flatten or the volume change somehow. And as a result of that, the graphene network that's conducting the charges will be deformed, which will make it more difficult for electrons to move around in that network, which not surprisingly results in an increase in resistance. However, because, as Jay mentioned, we're using a very mobile network because of this only 1 second relaxation timescale for the Silly Putty, you'll see relaxation relatively quickly, and the resistance will begin to lower again as the network reforms. However, if we try and constrain the amount of deformation by taking a flat disk like we're doing in our measurements, then instead of deformation being the main mechanism, you'll see that the network is instead compressed overall. So that compression is going to lead to a higher current instead, as the network is more conductive. Okay, so to start testing, we first looked at that commercial FlexiForce sensor. So this is just like a simple pressure sensor, relatively low cost, that's used in general applications. You apply a normal force, and the resistance will start from really high, like a mega ohm range, and drop down, and you see the current increase at a constant voltage of 5 volts, which is what we're using. So in black, you can see the input force that we were putting in. That's the normal force. And you can see as we were inputting the force, the resistance was changing to match the input force, and the current was increasing appropriately. So this is the sort of response we'd want to see from any sensor, a close match between the input and output. If you look at our G-Putty, which is using the same 1 centimeter diameter and a less than 1 millimeter thickness, we can see a similar behavior with just a higher current because it's more conductive. And we see again, as we input the force, you see a little bit of relaxation as the peak force drops down over the 2-second dwell time you're holding the load. But again, you can see in general an input is closely matches an increase in current. However, we're interested in looking at blood pressures that are a lot smaller than the forces we're applying. So in that last test, we were looking at around 1 pound force, which, to give you some intuition, is around 7 times what you'd need to actuate a keyboard button on most keyboards. So now at a blood pressure level, we're looking more around 0.18 for being able to sense really, really small movements. And if you look at the FlexiForce sensor, which isn't really designed for applications like this, you can see it's struggling to resolve that small change in pressure. And we no longer see that current increasing as you apply the input force. However, if you look at our G-Putty sensor, you can see even with really, really small deformations, you can see the current is still increasing appropriately, just because this using a nanocomposite will give you a lot more sensitivity and flexibility in that aspect. So as exciting as it was to see that the sensor is behaving the way we wanted it to, there are definitely some limitations to using a hybrid viscoelastic sensor like this. So one is the same sort of trade-offs you'd see with any sensor. The more sensitive you're making the sensor, or by adding this conductive filler, the less you'll see the properties of viscoelasticity that the Silly Putty is lending it. So there's a range in which the sensor will behave the way you want it to. And if you go too far in one direction, it'll behave more like a powdery solid. If you go too far in the other direction, then it will no longer be conductive. Another, even more important limitation is this relaxation timescale that we keep mentioning. So if you're looking at heart sensing applications, generally you're looking at a long range of time, because a lot of the problems you'll see in health that are related to heart problems are over long scales. In 1 second, you might be able to look at 1 heartbeat, but you can only get so much information from 1 heartbeat. And outside that 1 second time scale, you start to see this really big change in resistance over time. And that makes it really hard to get an absolute measurement when you're looking at like 10-second time scales, for example. One of the ways you can address this is by using signal processing, and we'll talk a bit about how some of the approaches that we use for that.
So in conclusion, we were successful of fabricating a flexible, conformable, and sensitive sensor that's sensitive enough to measure pressure as low as 40 millimeter Hg. And we were able to create a functional sensor with relatively low cost. But one of the main challenges that we encountered was graphene preparation, because we had to tip sonicate for 72 hours, and the solution itself was prone to overheating.
So again, going back to this application as a heart sensor, which is what we originally envisioned for this sensor, our approach that we kind of imagined for one of the ways to address this relaxation problem, there's a lot of different applications like this where you see drift or relaxation is a problem when you're looking at the integrity of your signal. So digital signal processing is generally pretty powerful in being able to extract useful information from non-perfect signals. So you can imagine if you took the signal that we get from the sensor that we've designed with the drift superimposed on it, and then use something simple like a Fourier transform that would take the signal in time, convert it to the frequency domain, and then allow you to extract fundamental information about the frequency of this periodic wave you're expecting to see. Combining that with peak detection would allow you to reconstruct the wave using a sum of sinusoids, and you can essentially try and predict what the long-term heart rate will look like with only 1 second of data. Of course, this is still not ideal because you still don't learn information about what could happen 10 seconds later. And if, for example, your heart skips a beat, you won't be able to model that in a reconstructed signal. There's a lot of other different methods you could approach, but in general, I think like a short-term arrhythmia diagnosis would probably be more feasible than long-term for this sensor. So finally, we'd like to acknowledge all the help we've gotten to get this far. So first, of course, Professor Maheshwari for lending his expertise and, of course, his lab space as well. It definitely wouldn't have been possible without him. Velocity for letting us use their equipment. And Dr. Coleman and his team at the Trinity College Dublin, who were the first to demonstrate the potential for a nanocomposite like this, and for helping us when we needed it as well. So if you have any questions at this time, we'd be happy to answer them.